Okay, finishing up lesson 9.6, we're going to do the rest of the examples. So starting with number 6, we have logarithmic equations. In part A, we have the natural log of x equals 8. Well, the natural log has a base of e, so whatever your log base is, you're going to apply an exponential base of the same thing on both sides. So since my log base is e, I'm going to apply an exponential base on both sides. So this will end up being e to the natural log of x equals e to the 8th. Again, natural log has a base of e, and because the exponential base and the log base are the same, it'll be equal to what you're taking the log of. So we end up with x equals e to the 8th, which is 2,980.958. And that will be our final answer. For part B, again, we have a logarithmic equation here because I have a log in the equation. So it's log base 2 of 25 minus x equals 3. Now my base is 2, so I'm going to apply an exponential base of 2 on both sides. So we end up with 2 to the log base 2 of 25 minus x equals 2 to the 3rd. Then again, because my exponential base and my log base are the same, it'll equal, this side will simplify to what I'm taking the log of. So I end up with 25 minus x equals 2 to the 3rd, which is 8. I can evaluate 2 to the 3rd equals 8. Then I subtract 25 from both sides, because now I'm just solving for x, and I end up with a negative x equals a negative 17. Divide by negative 1, and x equals a positive 17, and then that is my final answer. Looking at number 7, we have 4 plus 3 times the log of 2x equals 16. Again, this is a logarithmic equation because I have a log in it. But in this case, I have a 4 and a 3 on the outside. What I want to do is I want to isolate just the log. So my first step is going to be to subtract 4 from both sides. Then I end up with 3 times the log of 2x equals 16 minus 4 is 12. Then again, I'm still trying to isolate the log of 2x, so I have to get rid of the 3, so I'm going to divide both sides by 3, and I end up with the log of 2x equals 12 divided by 3 is 4. Now this log does not show a base, but a log with no base has a base 10. So I'm going to apply an exponential base of 10 on both sides. So we end up with 10 to the log of 2x equals 10 to the 4th. Now again, my exponential base and log base are the same, so this side will simplify to the 2x. So I end up with 2x equals 10 to the 4th, which we can evaluate to be 10,000. Then I'll divide both sides by 2, and x ends up equaling 5,000. And then that is my final answer. Looking at number 8, I have the log of x plus 2 plus the log of x minus 1 equals 1. Now, in this particular case, I have 2 logs on one side of the equation, and we don't like that. We want to have just one log on either side of the equal sign. So I'm going to simplify or condense these logarithms into just one. Since I am adding, I'm going to multiply the x plus 2 and the x minus 1. So I end up with the log of x plus 2 times x minus 1 equals 1. Now that I only have a single logarithm on one side, I can see that the base is 10, and I'm going to apply an exponential base of 10 on both sides. So I end up with 10 to the log of x plus 2 times x minus 1 equals 10 to the 1st. Again, since my exponential base and my log base are the same, I end up with x plus 2 times x minus 1 equals 10 to the first is just 10. I have to distribute or FOIL those, so I end up with x squared plus x minus 2 equals 10. Because I have an x squared, it indicates I'm going to have to factor. When we factor, the equation has to be equal to 0. So I'm going to subtract 10 from both sides. We end up with x squared plus x minus 12 equals 0. Then I have to find two numbers that will multiply to negative 12 and add to 1. Those numbers would be 4 and negative 3. So that gives us x plus 4 times x minus 3 equals 0. So then we end up with x equals negative 4 and x equals 3. We have to check our answers because remember we can't take the log of a negative number. Now we could end up with a negative solution, but not if it causes us to take the log of a negative number. So x equals negative 4 does not work. However, x equals 3 will work. So our only solution is x equals 3. Looking at number 9, again it's a logarithmic equation because I can see that there's logs. On the left side of the equation, I have two logarithms. Because I have two logarithms on the left side, I need to simplify or condense them to a single logarithm. Since I'm adding, I will multiply the x and I will multiply the x plus 1. So we end up with log base 11 of x times x plus 1 equals log base 11 of 6. Now I end up with a log base 11 on both sides of the equal sign. When you have a log with the same base on both sides, they really just kind of cancel out. So on this side, I end up with x times x plus 1 equals 6. I have to distribute over here, so I end up with x squared plus x equals 6. And then because I have an x squared, it indicates I have to factor. Because of that, I need the equation to equal 0, so I subtract 6 on both sides. Then we end up with x squared plus x minus 6 equals 0. And again, now I need two numbers that will multiply to negative 6 and add to a positive 1. Those numbers are going to be 3 and negative 2, because 3 times negative 2 is negative 6, and 3 plus negative 2 is 1. That gives me x plus 3 times x minus 2 equals 0. So I would have x equals negative 3 and x equals 2. We have to check our answers. If I plug negative 3 into the very first logarithm, I would have log base 11 of negative 3, and we cannot take the log of a negative number, so that solution will not work. Then we end up with x equals 2. And x equals 2 is our only solution because x equals negative 3. We actually called this solution extraneous. So the x equals negative 3 is an extraneous solution. It's like an extra solution, a solution that does not work. You can solve and get it, but then it doesn't actually fit. So x equals 2 is our only solution. For number 10, it says how long would it take $10,000 to grow to $15,000 if it is in a savings account that pays 2.59% interest compounded continuously? Because it tells us that our interest is compounded continuously, that means that we have to use the equation PERT. So A equals P times E to the RT. Again, I like to list out what everything is. So I like to list out the variables A, P, R, and T. So A is how much you have after time. So after time, we're going to have 15,000. So A is 15,000. P is your initial amount, and we started with 10,000, so that's P, that's your principal. R is your rate, so my rate is 2.59%, but it has to be a decimal, so that'd be 0.0259. And then T, it actually says how long, so T is what we're looking for. So then I plug these variables into the equation. So I end up with 15,000 equals 10,000 times e to the 0.0259 t. To solve for t, t is an exponent, so I'm dealing with an exponential equation here. So what I'm going to need to do is I need to isolate the e to the 0.059 t. So I'm going to divide both sides by 10,000. When I do that, I end up with 1.5 equals e to the 0.0259 t. Again, this is an exponential equation with an exponential base of e. So in order to solve this, I need to use a log with a base of e, which in this case is natural log. So I'm going to apply a natural log to both sides. So I end up with the natural log of 1.5 equals the natural log of e to the 0.0259 t. Again, since natural log has a base e and my log base and exponential base are the same, this side will simplify to the exponent. So we end up with the natural log of 1.5 equals 0.259 t. I'll divide both sides by 0.259, and then we end up that t equals 15.66 years. And then that is your final answer. All right, last example, looking at number 11. Number 11 says potassium-40 decays to argon-40 with a half-life of about 1.5 billion years, making this decay suitable for dating the oldest rocks on Earth. If 35% of the potassium-40 found in a rock has decayed to argon-40, about how old is the rock? This is a half-life equation, and our half-life equation is y equals a times 1/2 to the t divided by t sub 1/2. Again, with these, I like to list out what we have. So we have y, which is how much you have remaining, a, which is how much you started with, t, which is time, and t sub 1/2, which is your half-life. So if we look at this, it says that 35% has decayed, which means that you have 65% remaining. So what I like to do is I like to just say, okay, let's say we started, make it, when we're dealing with percentages, make it nice and easy. We're going to start with 100 grams. Since we have 65% remaining, 65% of 100 is 65, so our remaining amount would be 65. We're actually trying to figure out how old the rock is, so we don't know t, but we do know that the half-life is 1.5 billion, and then we plug everything in. So we end up with 65 equals 100 times 1/2 raised to the t divided by 1.5. My variable is attached to the 1/2, so I need to isolate this. So to do that, I have to divide by 100 on both sides. So we end up with 0.65 equals 1/2 to the t divided by 1.5. Again, this is an exponential equation because my variable is an exponent. My exponential base is 1/2, so I need to use a log base 1/2 and apply that on both sides. So I'm going to have log base 1/2 of 0.65 equals log base 1/2 of 1/2 to the t divided by 1.5. Because my log base and exponential base are the same, it's going to equal my exponent. So we end up with log base 1/2 of 0.65 equals t over 1.5. In order to solve, I'm going to multiply both sides by 1.5. We then end up that t will equal 1.5 times the log base 1/2 of 0.65. So then t equals 0.932 billion years, which ends up being that t will equal 932 million years old, which means that the rock is 932 million years old, which is a really old rock. Okay, that's it for all of the examples in 9.6, and that's actually it for all of Unit 8. Okay, that's it.